Hello and welcome to Awesome Day 2023. My name is Aarti and I have the pleasure of being your AWS technical trainer for this next session, Introduction to Networking and Security. So if you're new to AWS or just looking to learn more about networking and security in the cloud, you are in the right place. So jumping right in, let's talk about networking. At the heart of networking in AWS is Amazon Virtual Private Cloud, or VPC. VPC is a service that allows you to create your own private space within the AWS cloud, a logically isolated virtual network that you define. You can use VPC to logically separate your workloads, whether you're isolating your development, test, and production environments, or separating differing functions due to security concerns. VPC helps you control the flow of your traffic. VPC, like most other AWS services, is logically defined. Therefore, you can deploy as many VPCs as you need for your particular use case. It is not uncommon for larger, more complex environments to have hundreds of VPCs. Ultimately, it gives you control over the network access to your workloads, whether that be public access to the internet or private access only to your on-premise or corporate environment. When deploying a VPC, the first thing we need to do is to allocate a range of IP addresses. We can then further partition the VPC into smaller networks called as subnets. This allows us to break our VPC into segments which we can use for high availability or security or apply different levels of control. For example, here we have two types of subnets, public and private. The public subnets can be accessed via the public internet. Now you might just want to have a public-facing web application here, or maybe a Bastion or a jump host. We also have private subnets which do not have direct public internet access. This means they are protected from bad actors on the internet trying to compromise your application. This lets you place your backend systems such as databases or application servers in the private subnet with no internet access. VPC is what we call a regionally scoped service, meaning it sits across all availability zones within the region. Subnets are availability zone scoped, meaning they'll sit in individual availability zones. However, you can have multiple subnets in different AZs in a single VPC. You can have multiple VPCs within the same region or different regions for that matter. However, you cannot have a single VPC span multiple regions. So now that we know more about subnets, let's talk about how we can take advantage of the different VPC features to achieve a defense in-depth approach. When we design our infrastructure, we can achieve defense in depth. What this really means is that we have multiple layers of protection across the configuration of your VPC. Within your VPC, you can use these multiple layers of security, including security groups, network access control lists, and route tables to help control access to Amazon EC2 instances in each subnet. Firstly, we have an internet gateway that enables the resources in your public subnets, such as EC2 instances, to connect to the internet if your instances have a public IP address. Then we have the route tables. Route tables contain a set of rules called routes that are used to determine where the network traffic is routed. Using the route tables, we can protect our workloads to not allow public internet access or to restrict to outbound requests only. For the public subnets, the route table must have a route that directs the internet-bound traffic from your EC2 instances to the internet gateway. Next, surrounding the subnets, we have network access control lists. These are stateless packet filters that wrap around the subnet and determine whether traffic can enter or leave. These are great for providing explicit block rules to known problem areas or restrict specific protocols or port numbers. Next, wrapping around the EC2 instance is the security group, which acts as a stateful packet filter or firewall controlling the inbound and outbound traffic at the instance level. By default, all traffic inbound is blocked, while all traffic outbound is allowed. Lastly, on your EC2 instance itself, you can install your own firewall and protection software. In this demo, I will show you how to deploy a photo sharing website using Amazon S3, Amazon DynamoDB, and Amazon EC2. This demo will give you a holistic view of architecting an end-to-end solution by integrating the different AWS services we have talked about today. Let me walk you through the core architecture of the solution. First, our photo sharing website is deployed to a web server hosted on an EC2 instance. For this demo, I will act as the user who will upload an image through the website interface. The web application receives it and creates a thumbnail of the image. It then uploads the source image and the thumbnail to the S3 bucket and inserts the image metadata into the DynamoDB table. For the purposes of this demo, the media content is limited to images, but the concepts covered here can easily apply to other types of media content. Let's now build our demo. The first task is to create an S3 bucket to store the media contents and configure its permissions. At the top of the AWS Management Console, in the search bar, search for S3 and choose S3 from the dropdown. This takes us to the S3 dashboard. Choose the Create bucket and configure the bucket name, something like ANMyBucket2023. By default, content stored in Amazon S3 buckets cannot be accessed publicly. For our use case, we need to allow public access to the bucket so users can download content. So under the Block Public Access settings for this bucket, deselect the Block All Public Access. Acknowledge the security warning by selecting I acknowledge that the current settings might result in this bucket and the objects within becoming public. Scroll down and choose Create Bucket. While we want to allow downloads from the bucket, we don't want to allow users to list the contents of the bucket or delete any objects. Amazon S3 enables you to manage access to the objects and the buckets using bucket policies to configure permissions. We will now go ahead and create a bucket policy to configure the permissions for our S3 bucket. In the list of buckets, we choose the name link for the bucket that we just created. Choose the Permissions tab. In the Bucket Policies section, choose Edit. I will now copy a policy document and paste it in the policy pane. Choose Save Changes. We have now created an S3 bucket to store the media contents and configure its permissions. Next, let's create the media database to store the metadata information for our media files, such as the title, the comment, the publication date. Since we want our system to be scalable, we will use Amazon DynamoDB to store the metadata information. At the top of the AWS Management Console, in the search bar, search for DynamoDB and choose DynamoDB from the drop-down list. Choose the Create Table, then configure the table name as My Table, the partition key as EIB, and click on Create Table. The table we created is listed under the Table section and its status displays as Creating. The next task is to create our web server and deploy our photo-sharing website to the web server. But before we launch the EC2 instance, we need to create a basic Amazon Virtual Private Cloud, or a VPC. This VPC will be used to launch our EC2 instance. So in the AWS Management Console, in the search bar, type VPC, select VPC from the drop-down menu. We're now going to create a VPC with a single public subnet. The web server will be hosted in the public subnet so that it can reach the public internet. In the left navigation pane, choose your VPCs, choose Create VPC, and then configure the options. We're going to choose VPC only. I'll give this a name, Awesome Day VPC. Now the first thing we need to do is to allocate an IPv4 CIDR block as 10.0.0.0/16. Choose Create VPC. Our VPC has now been created. The next step is to create a public subnet. Next, in the left navigation menu, choose Subnets. Choose the Create Subnet and then configure the VPC ID as the Awesome Day VPC that we just created in the previous step. Give a public subnet a name, Public 1. For the availability zone, select the first AZ in the list. And for the IPv4 CIDR block, choose 10.0.1.0/24. Now scroll down and choose Create Subnet. Next, select the subnet we just created, namely the public one. In the Actions menu, select the Edit Subnet settings and then configure. Select Enable Auto-Assign Public IPv4 Address. Now, enabling this auto-assigned public IPv4 address, it provides a public IP address for all the instances launched into the selected subnet. Choose Save. Now, even though your subnet is now labeled as Public 1, it's not yet a public subnet. A public subnet must have an internet gateway attached to it, which we will create in the next task. In the left navigation pane, choose Internet Gateways, choose Create Internet Gateway, then configure a name for the gateway. Let's call it my IGW. Choose Create Internet Gateway. In the Actions menu, select Attach to the VPC and then configure from your available list of VPCs, you're going to choose the AWSOME Day VPC. And we're going to choose Attach Internet Gateway. This is now attaching the Internet Gateway to the VPC that we just created. Now, even though we've created an Internet Gateway, attached it to our VPC, we still have to tell our instances within the public subnet how to get to the Internet. So in the next task, we're going to create a route for the Internet-bound traffic. For this, from the left navigation pane, let's choose the route tables. We can see that there is currently one default route table associated with our VPC, the AWSOME Day VPC. Within the routes section, in the lower half of the page, notice that there is one route in your route table that routes the traffic locally. That is, it allows the traffic within the 10.0.0.0/16 network to flow within the network, but it does not route the traffic outside of the VPC network. We will now add a new route to enable public traffic. For this, choose Edit the Routes. Next, add a route, then configure the destination as 0.0.0.0/0. Choose the target as the Internet Gateway, and in the drop-down box, select the displayed Internet Gateway ID that you created in the previous step. Now choose Save Settings. Next, choose the Subnet Associations tab. Under the section Edit the Subnet Association, choose Edit Subnet Associations. Select our subnet public 1 and choose Save Associations. And now our subnet is public because it's connected to the internet via the Internet Gateway through the route in the route table. The next task is to add a security group so that users can access your web server via HTTP. Now, we discussed earlier that a security group acts as a firewall for your instance to control the inbound and outbound traffic. Again, from the left navigation pane, we're going to choose Security Groups. Choose Create Security Group. Give the security group a name. Let's call it Web Server Security Group. The description, allow HTTP traffic, and choose our VPC, which is our AWSOME Day VPC. And under the inbound rules, choose Add a Rule. The type is HTTP, and the source is traffic coming from anywhere. Scroll to the bottom of the screen and choose Create Security Group. The security group is now successfully created. When we launch an EC2 instance in the next task, we're going to associate this security group to the EC2 instance. Moving on to the next task. Again, from the AWS Management Console, using the search bar, let's search for EC2 and select EC2 from the drop-down menu. From the left-hand side menu, select Instances and then choose Launch Instance. From here, we will go through and configure the launch details of my new instance. I'll give this instance a name, which will be my photo sharing website or my website. Next, select the Amazon Machine Image, or AMI, which provides the information required to launch an EC2 instance, such as the operating system. Notice that we have a quick start here. The quick start list contains the most commonly used AMIs. You can also create your own AMI or select an AMI from the AWS Marketplace, an online store where you can sell or buy software that runs on AWS. In this case, we'll choose the latest version of Amazon Linux 2. Next, we're going to select the instance type. Since this is a simple web application, we will choose an instance type that is most appropriate for a simple, typical web server. We will go with T2.micro, which has one virtual CPU and 1 GB of memory. In the key pair section, locate the key pair name drop-down menu, and we will choose Proceed without a key pair. Now, something to note here, Amazon EC2 uses public key cryptography to encrypt and decrypt login information. To log into your instance remotely, you normally require a key pair, and when you log in, you specify the name of the key pair when you launch the instance and provide the private key to connect to the instance remotely. However, in this example, we will not be connecting remotely to the instance, so we don't require a key pair. Next, in the networking settings section, choose the Edit button, make the following selections. We're going to choose the VPC with the name that contains the AWSOME Day VPC. For the subnet, we're going to choose a public subnet 1. In the Firewall Security Group section, we're going to choose our security group that we created, the Web Server Security Group. Next, we configure the storage section. We can leave the default choices in here and for all the remaining configuration settings. Now, Amazon EC2 stores the data on a network-attached virtual disk called the Elastic Block Store. You will launch this Amazon EC2 instance using a default 8 GB disk volume. This will be your root volume, which we also refer to as a boot volume. Next, expand the Advanced Detail section, scroll down to the IAM Instance Profile, And in the drop-down menu, choose the Amazon SSM Managed core role. Now, I pre-created this role, and this role is simply associated with IAM policies that grants any application running on this EC2 instance, giving it permissions to access both Amazon S3 and Amazon DynamoDB. Next, scroll down to the termination protection drop-down menu and set it to Enable. Now, this is going to prevent your instance from being accidentally terminated. Scroll all the way down to the bottom until we see a field called User Data. Now, when you launch an EC2 instance, you can pass the user data to the instance, and that can be used to perform common automated configuration tasks and even run scripts after the instance has been launched. Your instance is running in Amazon Linux, so you will provide here a shell script that will run when the instance starts. I'm going to copy a pre-written script and paste it into the user data field. Basically, this script initializes a Ruby on Rails environment for the application that's going to be deployed on this EC2 instance. Then I'm going to deploy the web application to the initialized environment and then activate the web server. We've now done all the configuration, and we can choose Launch an Instance. Choose View All Instances from the bottom of the page. This takes us back to the EC2 instance dashboard. And you can see that the instance that you just launched might appear in a pending state, which means that it is just being launched. It will soon change to running, and that indicates that the instance has started the process of booting up. Now, when creating a new instance, there will usually be a short time before you can access the instance. Wait for your instance to display the instance state as running and shows a status check as 2x2 checks passed. Okay, so now our EC2 instance has been successfully launched. Let's go ahead and test our deployment. Let's select our newly created instance. And from the Details tab in the bottom section of the page, we can see the detailed information about your instance. We can see the instance type, the security settings, the network settings, and more. Let's locate the public IP address value and copy it to the clipboard. Let's open a new browser tab and paste the public IP address into the address bar and press Enter. We can see that our photo sharing website has been successfully launched. Let's now add an image to the application by choosing New, then providing a title, description, and tags. Add the image file and choose Create a Flick. Let's jump across to the DynamoDB dashboard. From the left navigation panel, choose Tables, choose My Table, choose Explore the Table Items, and we can see that the metadata of a media file is now, as stored by the web application, is now in the DynamoDB table. We can also check how the media files have been stored in the Amazon S3 bucket. Let's quickly navigate to the S3 dashboard, choose the name link of our bucket that we created, ANY bucket 2023, and we can see the list of image files uploaded by the application in the bucket, along with the thumbnail image that you can recognize with the tn.png extension. Congratulations, we have successfully deployed and tested our web application. In the above solution, we have seen how to deploy a photo sharing website using Amazon EC2, Amazon DynamoDB, and Amazon S3. While Amazon S3 and DynamoDB are both scalable and fault-tolerant systems, the web application running on a single EC2 instance is clearly a single point of failure. If the web application fails, the system is not accessible and cannot recover, and remains a bottleneck. With a large number of load incoming requests, the system might even become unavailable. For better resilience, we could have built the same example, employing an event-driven architecture, making use of Amazon S3, Amazon DynamoDB, and using AWS Lambda as the compute service in place of EC2. Okay. In a small environment where you have a low number of instances, maybe 1 or 2 instances, the traffic distribution is not going to be a problem. But what happens when you want to scale that out or have dynamic scaling that changes depending on how much load is currently being produced? We need a more sophisticated load distribution method. Introducing Amazon Elastic Load Balancing Service, or ELB. Amazon ELB comes in multiple flavors, but the key here is the application load balancer that distributes traffic according to HTTP or HTTPS rules that you configure. Elastic load balancers are highly available and can be used to decouple application tiers. This means your web tier doesn't need to be aware of changes to the app tier infrastructure. It also supports health checks. So if instances behind the Elastic load balancer fail, or maybe your application stops responding, the ELB can actually determine that a particular instance has failed. It will then stop distributing traffic to that failed instance, resulting in a better experience for your customer. Then finally, we also get security features within the Elastic load balancer. We can utilize TLC termination on our Elastic load balancer to unburden our instances behind the scenes. Now, the Elastic load balancer is regionally scoped. It gives us the ability to distribute incoming traffic to multiple instances or applications across multiple AZs within the region. But what if we want to distribute traffic across multiple regions? Amazon Route 53 gives us that capability to do that on a global scale. Amazon Route 53 is a highly available and scalable cloud DNS service. You can use it to register domain names and even perform automatic renewals or configure different routing options which allow us to determine where the traffic should go. It provides tools for flexible, high-performance, highly available architectures on AWS, and we have multiple routing options. Let's see how this works. In this particular example, we might have a client or an end user that's trying to connect to our application that is sitting within our VPC. The end user would navigate to our website URL. Route 53 would then be used to resolve that URL into an IP address, which then leads us through our internet gateway to our Elastic load balancer, which then distributes the incoming traffic to the multiple EC2 instances sitting behind the load balancer, which then could respond back to the user. And we're doing this all within our VPC within the AWS cloud. Amazon VPC also offers connectivity over VPN or using another service called as Direct Connect, which allows you to connect to your VPC from your on-premise data center, offices, or other customer locations in a secure manner. In addition to these hybrid connectivity options, VPCs can also be connected to each other through a mechanism called VPC peering, and these VPC peering connections can span multiple regions. So we have the ability to peer VPCs together to expand our environment if necessary. Okay, so in summary, we have learned that Amazon VPC allows for the creation of logically isolated network to launch applications. Within your VPC, you can use multiple layers of security, including security groups, network access control lists, and route tables to help control access to Amazon EC2 instances within the subnet. Finally, for hybrid networks, AWS offers different connectivity options such as site-to-site VPN and Direct Connect to connect your on-premise data centers to the VPC in the cloud. We'll now change directions and talk about security. At AWS, cloud security is our highest priority. As an AWS customer, you will benefit from a data center and a network architecture that is built to meet the requirements of the most security-sensitive organizations. The AWS infrastructure has been architected to be one of the most flexible and secure cloud computing environments available today. A key way to look at security on AWS, especially as a customer, is using this shared responsibility model. When you think about security in your on-premise environment, well, you need to manage everything, from the physical security of the building to the physical security of the IT devices, through to environment controls, operating system, application, data, etc. This results in a considerable amount of administrative overhead without much benefit added to your business. We previously talked about the term undifferentiated heavy lifting, which referred to running the physical components of the data center. When deploying resources on AWS, we learned that the AWS took care of this undifferentiated heavy lifting. That is, AWS will manage all that physical stuff for you. This means that AWS has some responsibilities in keeping the cloud secure. On the flip side, AWS does not have access to your data. We also don't have access to the resources you deploy. So there will be an element of responsibility that falls onto you as a customer. And this is where the shared responsibility model comes in. It details and highlights what is AWS responsibility and what is your responsibility. Let's take a look at two simple examples. Firstly, when using EC2, it is AWS's responsibility to provide physically secure compute servers that are made available for use. But then, when you deploy on an EC2 instance, it is your responsibility to apply ongoing operating system patches. It is the responsibility of AWS to provide the ability to encrypt your EBS volumes. However, it is your responsibility to actually enable the encryption. We don't mandate how you must perform something. We provide you the options, the levers, and controls. In a separate example, let us look at S3. It is the AWS responsibility to provide a highly available and durable storage solution for you to use. It is the AWS responsibility to provide a permission structure that restricts public access. However, it is your responsibility as a customer to determine what data resides in S3, whether you want this data to be encrypted or not, and which identities have access to it. In short, AWS is responsible to provide a robust and secure cloud framework, a framework that provides you, the customer, the ability to operate safely and securely. But it is your responsibility to make use of this configuration options, the levers, and the controls to appropriately decide which data can reside where, and then to make informed decisions on how to deploy your services. Every service in AWS falls into the shared responsibility model. Some services are going to require more responsibility from you as the customer, whilst others require less. There are many services that can help you manage your security, from encryption to key management to web application firewalls, logging and monitoring, just to name a few. Let's now talk about how we can use the AWS service, Identity and Access Management, or IAM, to authenticate users and control their access to the different AWS services and resources. AWS IAM gives you the ability to securely control access to your AWS resources. You can assign granular permissions to users, groups, and roles. You can share temporary access to your AWS account and also federate users from your corporate network or with a web-based identity provider. Let me now take you through some whiteboarding to understand the core components of IAM. AWS Identity and Access Management, or IAM, is a service that helps you to securely control access to AWS resources. You use IAM to control who is authenticated or signed in and who is authorized or has permissions to use the AWS resources. Authentication is establishing the identity of the caller accessing the AWS resource. And in AWS, we refer to this caller as a principal. Authorization is establishing the permissions of the authenticated principal. What can they access? A principal in IAM can be a single IAM user. Let's call our user Shirley. Or it can be an IAM group. Here we have a group of users, Shirley, Bob, and Mary, belonging to the group developers, or a principal could also be an IAM role. Now, an IAM user is a permanent identity. You create it, and the credentials will stay until you choose to remove them. There are two ways a user can authenticate: via a username and password to log into the graphical AWS Management Console, or via an access key ID and secret access key through the CLI or SDK. Now, when we create an AWS account, we begin with one sign-in identity that has complete access to all AWS services and resources in the account. This identity is called the AWS Account Root User, and this user is the first user, which we refer to as the root user. Now, here are some key AWS security best practices. First and foremost, enable multi-factor authentication on the root user credentials. And do not use the root user credentials for your everyday tasks. Instead, logged in as the root, create an administrator user with a ** privileges, and then use the administrator user to perform your day-to-day tasks. We do this to safeguard the root user credentials. Now, an IAM role, on the other hand, is a temporary identity, which can be assumed for a short period of time, after which it will automatically expire. Now, when you assume a role, you are granted a temporary set of access keys that have a defined expiry period. Roles are extremely powerful and allow you to create identity federation, where you can create a single sign-on experience for your users or even customers. Using roles, IAM could be used to grant the employees in your organization and applications federated access to the AWS Management Console and the AWS Service APIs by using your existing identity systems, such as the Microsoft Active Directory or an LDAP identity store. Now, in AWS, we talk about implementing the principle of least privileges, which is all about granting users just the right amount of permissions they need for these AWS services and resources they need to access. Permissions are granted to a principal using policies. Now, when the authenticated principal Request to perform an action. Example, view an object in the S3 bucket. The policies enforced on the principal are evaluated to check if the principal can perform the requested action. Now, in AWS, a policy is a JSON formatted document that allows you to grant or deny actions. Actions are basically the REST API calls that are made to access your resources. Let's take a look at what a policy looks like. Now, each policy statement in the policy document, it consists of 3 key elements. The E stands for effect, which can be an allow or deny. The A stands for action, the specific REST API call, example, the getObject API call on the S3 bucket. And the R stands for resource, the AWS resource that you want this particular policy to be applied on. For example, let's create a policy statement where the effect is allow, the action is start instances, and the resource is EC2 star, meaning all the EC2 instances. Let's call this policy the EC2 launch policy and attach this policy to our user, Shirley. Let's go ahead and create a second policy that allows access to all API calls on the EC2 web service on all the EC2 instances. We're going to call this the EC2 admin policy and attach this policy to our developers group. So, my question to you, what is the net access control for Shirley? Well, Shirley is firstly able to launch any EC2 instance because of the EC2 launch policy, but as Shirley is also a member of the developers group, which has the EC2 admin policy attached to it, Shirley can invoke any action or any API call on the EC2 service. The policies we just created are called as identity policies, as these policies can be attached to different kinds of principals, which can be a user, a group, or a role. Well, that's a quick overview of AWS IAM. We previously talked about using Amazon S3 for object storage. S3 is an example of a service that can have a resource-based policy attached to the bucket. In this case, we call that a bucket policy. A resource-based policy is just another type of IAM policy that is attached to the resource, such as an Amazon S3 bucket, and these policies grant permissions to the principal that is specified in the policy. Let's look at this example where you've created a new bucket. The default access configuration blocks all access other than the owner who created the bucket. But maybe you want the ability to grant permissions to everyone to make it public. This is useful if you have content that you want to share publicly, like our photo sharing website. But what if you want to just grant permissions to specific users or services, or maybe a subset of users, roles, or services? Bucket policies, along with identity policies that we spoke about previously, allow granular control over who or what can access your resources, from where and when. Another way we can ensure the security of our data is to utilize various forms of encryption on objects in a bucket. S3 offers server-side encryption, known as SSE, on the objects stored in the bucket, and you can do this encryption either by using a customer-provided encryption key, a key managed through the key management service, AWS KMS, or have the S3 service itself manage the encryption key. Using these forms of encryption enables S3 to encrypt your object when the data is at rest. S3 also supports the HTTPS protocol, which enables encryption in transit. Moving on to our next service, AWS CloudTrail. AWS CloudTrail is an example of a service that we can use for security auditing in our AWS account. CloudTrail enables us to track identity activity and API usage in our accounts. We can continuously monitor activities and record API calls against multiple different services in our account. We can use this for compliance, auditing, security analysis, and also for troubleshooting purposes. We can also use this to record in case we need to backtrack and understand how the access was granted. The API calls are stored in a trail, essentially a log file. These trails can also be exported to our S3 bucket that we talked about earlier. And so, by keeping all that information, we have the ability to answer common questions from a security standpoint about who made a request, what did they request, when did they make that request, and from where were they requesting. So CloudTrail gives us the transparency in our account. Additionally, storing the CloudTrail logs into S3 allows us to reduce the cost of storing that important log data and also grants us the ability to use various querying tools such as Amazon Athena, a serverless SQL querying tool. The last service I want to talk about in this session is AWS Trusted Advisor. Trusted Advisor is a tool that sits in the background of your account and provides guidance on how to improve your account across various pillars like security, performance, fault tolerance, and cost optimization, along with identifying any service limits you are approaching or might have hit. Trusted Advisor bases its guidance on the AWS Well-Architected Framework, a series of best practices compiled by AWS architects to help build effective architectures. So how does the Trusted Advisor work? Let's take an example of cost optimization. Imagine you have a large EC2 instance, an M5 4 extra large, and that has been operating at 10% utilization over the last month. Trusted Advisor may look at this and say, well, you can reduce the size of this instance and still meet your performance objectives, and it will cost you less so you can achieve some savings. On a separate note, maybe you have all of your EC2 instances in a single availability zone. If that availability zone were to have an issue, you could potentially lose your entire environment. So Trusted Advisor will give you a warning under the fault tolerance category, suggesting that you deploy your resources across multiple availability zones. There are many checks that Trusted Advisor performs, which are regularly refreshed to give you updates as changes to your account and environment are made. So summarizing what we have learned in the security module. Security is a shared responsibility between AWS and the customer. Customers should carefully consider the services they choose because their responsibilities are going to vary depending on the services used. We also talked about AWS IAM that enables us to implement a fine-grained access control to AWS services and resources. We talked about AWS CloudTrail, an AWS service that records actions taken by a user, a role, or another AWS service as events. Finally, we learned that AWS Trusted Advisor evaluates your account and provides recommendations that help you to optimize your AWS infrastructure, improve security and performance, and reduce costs. I hope you enjoyed the session and found it interesting. AWS is a data-driven company, and I'd like to take this opportunity to ask you to complete a survey telling us what you thought of the session. This can help us shape and improve events and learning in the future. You can also reach out to us on the various social sites listed on the slide. Why not test your knowledge and make sure you complete the knowledge check after the session to see how you are progressing? I would like to thank you all for attending this session. Next up, join my colleague Jack for Module 4, Innovation with AWS.